All right, guys, so today we're going to talk about limits, and this is a central concept to calculus. This is where you go from just algebra and pre-calculus into the idea of calculus. And this is due to the genius of Newton and Leibniz. They were the ones who started to study these types of concepts or these types of ideas. And it's the idea of dealing with quantities that are infinitely small, or dealing with quantities or functions at points where the function is not defined. You're going to be approaching things very, very closely. So how does it work? And of course, there's a formal definition for it, a mathematical definition for it, but we're not going to look at it. We're going to do it a little bit more intuitively. So let's take a look at a function that up until now may be completely unremarkable, but let's take a look at this. So that function there, in pre-calculus, you would have done this. And I want to believe that most of the instructors will, or professors will have told you, be careful before you cancel to see or to make sure that you are or make a comment that this only cancels on the domain of the function. So if you were to do the cancellation, you would have to be careful and say that this is true when x is not equal to positive 2. So when x is not equal to positive 2, this function is always equal to x plus 2. Always equal to it. But not at x equals to 2, because when x is equal to 2, the numerator becomes 0 and the denominator becomes 0. And we don't know how to divide by 0, much less do the cancellation 0 over 0 times 1. You cannot cancel. You don't know what happens there. So to prevent that, we had to have the caveat that x is not equal to positive 2, because then at that point we have an issue. So limits are going to allow us to consider those situations. So let me go ahead and erase this, and I'll tell you roughly what the limit will be. So to motivate for it further, what you could do is see what happens with the function as you approach that value of 2. Obviously, we have a problem. But we're not going to do too many numbers because I don't like numbers. Imagine that. But you could approach 2 from the left or the right. And graphically, what you have, if you have x equals to 2 here, and you're trying to figure out what the function does as you get really, really close from the left and from the right. You want to find out what the function is doing as you're approaching it from both directions. So from the left, let's grab a couple numbers. So 1.9 and then 1.99. And from the right, let's say 2.01 and then 2.1. Oh, I was supposed to change colors to make it match. Oh, I'll do it. I'll be right back. All right, so at least you can see the colors now from the left and from the right. And you would compute the value. You know that if you plug 2 here, you don't get a number. Oops, that was supposed to be a question mark, not a 2. You don't get a number. You don't get a value, because you get 0 divided by 0. Oh my goodness, I'm making a mess. Let me erase and do a proper question mark. All right, so you know what happens there, but you can plug 1.99 because there's absolutely no problem. Now, I'm going to lie because I already have the answer, because I can plug it directly in here, because when you plug 1.99 and you factor it, you get 1.99 minus 2, which is going to be 0.01 negative, divided by negative 0.01. That does cancel, and you just get 1.99 evaluated here. So I'm going to have 3.99, and I'm going to have 3.9. But of course, you wouldn't do that for all examples. Some of them you'll have to put in your calculator. So I don't have one. I don't even own a calculator. Only the one on the computer. Isn't that sad? Yeah. Maybe I should get one day. But anyways, so the point being is that as you get closer and closer to 2, your value is getting closer and closer to 4. So you say that the limit, and this is the notation that we use, the limit, because I'm not saying that if I evaluate it at 2, I get 4. I'm saying that if I approach 2 on the x, the function f is taking the value of 4. I'm not saying that f of 2 is 4. F of 2 is undefined because I'm dividing 0 over 0. I'm saying that I can make sense of that value in the limit sense. So I can give you the value that the function is approaching, but I cannot tell you that the function takes that value. Now, if I wanted to find in this particular case this limit, say as x goes to 1 of this particular function, well, in this case, I can evaluate it and I get 1 plus 2, I get 3. But that does happen to be the same as the value that the function takes at 1. Why? Because I have no problems at 1. At 1, I do not have zeros in the denominator. I'm not trying to make sense of anything weird. I'm just plugging it in. So limits are gonna be useful for us to make sense of those kind of tricky situations. We have 0 in the denominators. We have things that are approaching asymptotes or like in the logarithm where you had a vertical asymptote. All those situations are going to be dealt in the limit sense. But why? And the question is, why are we trying to do this? So we're trying to make sense of these functions where they're not supposed to make sense. Well, sort of. But the reason why we're trying to do that is because if we think about a function, let me write this. So if we think about a function, let's say it has this shape. And let's say that we want to find out how fast the function is changing at that point right there. What we can do is we can grab points to the left and to the right of it. I'm going to make them somewhat separate. And I can draw lines connecting those points, sort of like this. And sort of like this. Oh, that's not a very straight line. And I can compute the slope of these lines. That's really ugly drawing. But I have another video where I made beautiful drawings, so I'll link that one as well. So I can go to the left and to the right of this point and find the slopes of the lines that connect points on the graph. And as I start approaching as I start getting closer and closer and closer to this point, and my points are very, very close to a point, the green point here, then my line eventually will become what is called a tangent line. And I explain that much, much more carefully in the next video. But I just want you to understand that we are interested in trying to make this distance smaller and smaller and smaller. And the way we do this is through the limit. Because if you look at this expression, you will see that you end up with a 0 in the denominator. And we want to make sense of what the function is doing when it approaches that 0 in the denominator. And without the limits, we couldn't do that. And that's where physics needed calculus, because this eventually will correspond to something that is called the instantaneous velocity. So that's where the idea of calculus comes from. Let's compute one more limit numerically, and then we'll leave it at that. Next time we'll do limits analytically or algebraically. So I'm going to erase, I'm going to do one more, and we'll come right back. All right, so let's do this one real quick here. So this is an example of one. I'm going to give away what's happening. This limit will not exist. I'm going to do the limit as x goes to 3. So find out limit as x goes to 3 of f of x. And how would I know that it doesn't exist? Because if I plug it in, I get 3 squared is 9, plus 2 times 3, so plus 6 is 15, divided by 3 minus 3, which is 0, so I get 15 over 0. I'm dividing an integer. It could be any real number, really, that is not 0, by 0. And that gives away the fact that the limit will not exist or will go to infinity. So we will just have to, we'll fill out our table to take a look at that. So as I told you, I don't have a calculator, but I have a phone. So I plugged it into my phone. So this gives me negative 142.1. So that is plugging 2.9 and plugging f of 2.9, which is going to be equal to 2.9 squared plus 2 times 2.9 over 2.9 minus 3. And I plug that in my calculator, and it gives me the answer, or my phone in this case. And I can evaluate it again at 2.99, and I get negative 492.1, but I cannot fit it. At 3, I don't know. I get a 15 over 0, but I don't know. That's a question mark. It doesn't look like a question mark. Having issues with my question mark today. Let me evaluate the other two real quick. So thankfully, I just put in a calculator where I can just change the name of the variable. I do recommend that if you know how to do that, you do that. The other way to do it is using Excel. So you can plug it in Excel. I have a video on how to do that, and I'll link it. There's a decimal expansion here, but I'm not going to put it in just because we don't have space. And then the last one is a 158.1. All right, so what is happening is that as you're approaching 3 from the left, as you see 2.9 is a bit further to the left, you're getting negative 142, let's say here. But as you get closer, so 2.99, you're going to 1,000. So this is going down in this direction. Excuse me. And then when you go at 3.1, so a little bit further to the right, you're going at 158.8. But when you get closer, you get 1,000. Of course, it's not run to scale, of course, but you go to 1,508. So it goes up in this direction. So you see the function will have a vertical asymptote there at x equals to 3 that is going to be going to negative infinity in one direction and positive infinity in the other. And we will be talking about those kinds of things in a few videos. So at the moment, we're going to leave it at that. In this case, we say that the limit does not exist. Technically, we will then, or in reality, what's going to happen is we're going to start considering the situation where you approach 3 from the left, and you say as you approach 3 from the left, you're going to negative infinity. And as you approach 3 from the right, let's say, you're going to positive infinity. But we will leave that to another video today when I just say does not exist. So thank you for watching, and I'll see you in the next one.